Alright, welcome to another video on shear force and bending moment diagrams. We have done a few examples already, and I have shown you how you can calculate bending moment and shear force equations based on the distributed loads themselves. So this is going to be a relatively quick video where I'm just going to show you all the steps that are already laid out here, and you're going to get a better idea of how to use combined or distributed loads that change across the length of the beam and how to analyze them. So the first thing we're going to do is we're going to draw this, we're going to split this up into three sections. So we have two triangular areas over here and a uniform distributed load in the middle. So we have the two sides here are going to be triangular areas of height 10 and of width 2. So they're going to be equal. The resultant force is going to be the area of those triangles, which is 10 kilonewtons. And that's essentially what you observe here. Then for this one, we have a rectangle of width 3 meters and height 10 kilonewtons per meter. So that's going to give us a resultant force of 30 kilonewtons. The next thing we know is that for a triangular distributed load, the centroid is always located at 1/3 from the total length here. So it is 1/3 from the vertical side. So in this case, that would be 1/3 of 2, which is 2 and 3. So if we take the distance from the left hand side over here, it would be 4 and 3. Then for this one, it's just going to be right in the middle, so it will be at 1.5 meters from each end, essentially. So now, if we add all of that and we express them as exact fractions, this is essentially what we get. And I think the good thing about this problem is that it has a lot of symmetry, so you'll see what the consequences of a symmetric distributed load are going to be. So we can calculate the resultant forces on these supports by taking first the sum of the moments about A. So we're going to have 7, which is the total length of the beam here, times reaction at B, minus 4 over 3 times 10. And then we have all of these moments here. Then we put them together, and it turns out that the reaction at B is 25 kilonewtons. Now what we notice is that the total force acting downwards is 50. So we can assume already that the reaction rate has to be 25. So this thing is in equilibrium. And that's not unexpected at all, because if you consider how this is symmetric about the middle of the section, we should expect both reaction forces to be exactly the same. Now, when it comes to drawing the shear force diagram, what we're going to do is we're going to look at each of these distributed loads. So over here we have a straight line, so we know that the shear force is the integral of the distributed load, and it is negative. So if this is a positive gradient, then this is going to have a negative kind of it is going to go downwards. So in here what we notice is, okay, so we can calculate the gradient from that straight line, and we can actually calculate that. So if we take the length from 0 to 2 meters over here, we can easily integrate that function, and then we get this parabola over here. And with that, what we can do is we can say, okay, so we know that the constant of integration will correspond to the reaction force on the left, which is 25 kilonewtons. And now we can evaluate using this function what the value of the shear force is going to be at exactly 2 meters, where the new distributed load changes, and that's going to be 15 kilonewtons. So we're going to end up over here. Now this is a concave down parabola, so we're going to come down like that. And then once we get here, we have a distributed load that is constant. So in this case, we could also figure out what the equation of this line is. But the truth is that we don't actually need to know that. And the reason for that is that we can figure out the areas over here. So remember, for the bending moment diagram, all we need to know is the areas on each of those sections. Now, since this is symmetric, we expect this straight line to cross the x-axis here at the middle of 7 meters, or 3.5. So these two areas, 2 and 3, that I have denoted here, are going to be equal. And similarly, once we get to this other triangular distributed load, since this gradient is negative, that means the shear force becomes positive, so it is a concave up parabola like this. And once we get to the very end, we're going to go up by 25 kilonewtons again. And that's going to be our shear force diagram. And it should be symmetric because it corresponds to this symmetric distributed load. Now, in order to calculate each of these areas, what we're going to do is we're just going to integrate. The parabolas we can integrate. So that's going to allow us to figure out what the bending moments are at each point. So for the first area and the second one, we know those two areas are going to be the same. The only difference is the sign. So we only need to calculate one of them. So in this case, calculating one, we just integrate this function here, then sub between 0 and 2, and that turns out to be 43.33 kilonewtons meters. So that's essentially what's going to be the value of the bending moment once it reaches 2. And then for each of these two areas, we're going to just use a triangular area, which can be found directly from the graph, and it is 11.25 kilonewtons meters. Now the next thing is to draw our bending moment diagram. So if we have a parabola here, then we know the shape would correspond to a cubic equation because the bending moment is the integral of the shear force. And since this is negative over here, we know that this is also going to have a negative kind of shape, so it's going to go like this. Now once we get to this part over here, what we're going to notice is, okay, so now we reached that maximum value, but now we're going to add this quantity to it. So by the time we reach the middle of the section, which is what's going to give us the turning point for the bending moment diagram, we're going to be at 54.58 kilonewtons per meter. And then since this problem is symmetric, we expect this to come down again like that. So that's our bending moment diagram. So we could have integrated each of these functions, but in general, we only care about the maximum bending moment at each of those points. So in this case, the maximum bending moment is 54.58 kilonewtons meters. And that's it. That's how you analyze a beam that has distributed loads that are discontinuous but change their shape and definition along the length of the beam.